Often I'm asked about the photobiological spectral bands, UVA, UVB, and UVC. People ask this because they hear about UVA being safe for sun lamps and things like that. But in actuality, all spectral bands have some risks to the eye and skin, but they do differ quite notably depending upon the CIE photobiological spectral bands. Now, you're probably going to ask, what's the CIE? That's the International Commission on Illumination, Commission Internationale d'Éclairage in French, which is where we get CIE. And back in the 1930s, the CIE Committee on Photobiology created the concept of these photobiological spectral bands and named the bands UVA and UVB and UVC. And these have remained as international standards without a change as over nearly a century. I think I want to first emphasize, though, that these are shorthand notations. Because if you really want to know about the hazard of any part of the ultraviolet spectrum, you want to know what we call the action spectrum to see what is the actual effect at different wavelengths. But in any case, the near ultraviolet, or UVA, extends from 315 to 400 nanometers, and this is often referred to colloquially as near ultraviolet radiation or as black light. You might see these in a disco or certain things for special effects for illuminating fluorescent posters and that sort of thing. That's where they comes with the name black light. UVB is the really dangerous radiant energy. It has higher photon energy than UVA, more energetic. Its spectral band runs from 280 nanometers to 315 nanometers, and this is often referred to as actinic radiation. It's highly photobiologically active and has been cited as the principal cause of skin cancer from sunlight. UVC, though, is blocked by the atmosphere, so we don't get UVC from the sun, and this is referred to as the germicidal band. It goes from 100 nanometers to 280 nanometers, or you'll often see it as from 180 or 200 nanometers to 280. But because that's the normal emission of the germicidal lamps. Visible light extends from somewhere around 360, 380 nanometers up to at least 780 nanometers. And a lot of people wonder, why do we have an overlap into the infrared and ultraviolet with what we consider visible? And that's because the eye is sensitive to very intense levels of UVA or very intense levels of near infrared, known as IRA. And so there's no fine line between where at a single wavelength you switch and suddenly everything becomes invisible. It doesn't work that simply. So IRA, or near infrared, goes from 760 or 780 nanometers up to 1400 nanometers. Beyond that, we won't talk about infrared here, but the dividing line between IRA and IRB gives you an explanation of why these have spectral band limits, because right around 1400 nanometers or 1.4 micrometers, water becomes suddenly very absorbing, so that none of that energy penetrates the eye at all, nor the skin. Then, if we want to talk about photobiological effects on humans, we can draw a little diagram as here, showing the different biological effects as a function of the UV band. So let's just concentrate on UV and not worry about the visible and infrared at the moment. Photokeratitis is possible all the way through UVC and UVB, but is almost impossible from UVA. There's a really sharp cutoff somewhere around 315 nanometers. Cataract appears to be limited to a fairly narrow crossover area between UVB and UVA, where there's enough photon energy to alter key biological molecules in cells, and at the same time, it also penetrates into the eye. Erythema or sunburn, as we see, is possible in the UVC and UVB. UVB is much more severe because of the deeper penetration into the skin than any type of mild erythema that might come from UVC wavelengths. Skin cancer is very difficult to define because of the fact that it takes so many years before it shows up. So it's very difficult to assess exactly what wavelengths a person received. But from a lot of laboratory evidence, scientists have posed that it's pretty much limited to a crossover section of UVB into the UVA, with a peak right around 300 nanometers. And the bottom panel shows the penetration depth relatively into skin as a function of wavelengths. And as you see, all of UVC and UVB is pretty superficially absorbed. It takes the near infrared before it really penetrates into the skin, as from a heat lamp. The last thing I'll mention here has to do with studies of the acute effects of UV on the skin. And what we see here are the results from a study that was conducted by Hauser and Walle at Siemens Company in Munich back in the 1920s and published in 1929. And the really fascinating thing to me is that this still is one of the best scientific studies, even though it's almost a century ago. It actually was done so carefully that it's been documented using laser wavelengths to be quite accurate. So the top little series of panels shows how the action spectrum, the relative sensitivity as a function of wavelength for reddening of the skin, appears even 2 or 3 hours after as a very, very mild reddening that can be just detected. At 4.5 hours, we find that a much more severe grade of erythema appears around 300 nanometers, and a milder UVC thing. Then we go to 6.5 hours in one day, and you see how the action spectra is changing depending upon when they assess the reddening of the skin. And after a few days, the effect of UVC has pretty well gone away, but they can still see a significant reddening of the skin at 4 days, 6 days, 10 days after wavelengths around 313 nanometers. Now, the bottom panel shows you the relative grade severity of the erythema as a function of wavelengths. And as you see there, 313 nanometers, which is the longer wavelengths, most penetrating wavelengths of UVB, cause the most severity just barely above the threshold. Whereas if we go to the other extreme shallow curve, labeled 254 nanometers in the UVC, it never gets beyond a grade 2.5. And it shows up much earlier than the longer wavelengths UVB. So it just goes to show that there's no simple action spectrum. It depends upon how deep the photons penetrate into the skin to really determine the time course of erythema. Thank you.